Good morning to all. Now we see the case study on numerical method for accelerating the convergence of the power method. Introduction. Eigenvalues arise in many physical problems. Some of the physical situations where eigenvalues are required can be listed. That is flexural acceleration of a tapered rod, vibrating problems, stability problems, bulking of columns, stability of electrical circuits, etc. While trying to analyze the solution to this type of problems, we come across eigenvalue problem. These physical problems require for their solution the values of lambda which satisfy the characteristic polynomial. That is p of lambda equal to determinant of a minus lambda y that is equal to 0. The problem we are considering is given an n by n real matrix A, find numerical approximation to the eigenvalues of and eigenvectors of A. The numerical eigenvalue problem is difficult to solve in general. In many applications, A, the given matrix may be a symmetric or tridiagonal or have some other special form or property. Consequently, most numerical methods are designed for special matrices. If lambda 1 is an eigenvalue of A, that is larger in absolute value than other eigenvalue, then it is called the dominant eigenvalue. An eigenvector v1 corresponding to the eigenvalue lambda 1 is called the dominant eigenvector. Therefore, the theoretical considerations for accelerating the convergence of iteration process involving matrices and with the test examples to overcome the basic unreliability of Aitken's method for a significant range of applications. Therefore, the Wilkinson described a technique for calculating the eigenvectors of a matrix automatically by means of the Lenkos transformation. This method can be made to give accurate results for both of Lenkos transformation. Then here the would describe and contrasted the structure and implementation of a new general iterative method for diagonalizing large matrices with the more commonly used iterative techniques. The method requires the direct diagonalization of only a small submatrix, does not require the storage of the large matrix, and provides eigen solutions to within a prescribed precision in a rapidly convergent iterative procedure. This technique makes possible efficient solution of a variety of the quantum mechanical matrix problems where large basis set expansion are required. Then Canbright introduced a fully distributed power method for finding the principal eigenvalue of arbitrary matrices that are stored in weighted lengths of overlay network. We address the problem of synchronization and normalization. Through the example of link analysis, we demonstrated both theoretically and experimentally that the proposed method is competitive with the power method. We can also demonstrate extreme fault tolerance. Then, those two people produced a new technique to improve and calculate the eigenvalues and eigenvectors of the linear system. The procedure is compared with the well-known power method. We already know the power method for finding the largest eigenvalue. Then we, including its condition L1 condition, the number and some observation of numerical test, two variant algorithm, that is standard power method and Aitken extrapolation method, which are based on the extrapolation method. Here, the convergence of power method is improved to calculate the greatest eigenvalues of any matrix by using Wilkinson's method and Aitken's method, and also suggested a new algorithm which combines between the Wilkinson and the Aitken's method in order to obtain the best approximation. Then first one, power method. Assume that A is a n by n matrix. It has a distinct eigenvalues, that is lambda 1 etc. lambda n. Then they are ordered in decreasing magnitude, that is lambda 1 less than lambda 2 less than or equal to lambda 3 etc. less than or equal to lambda n. We can choose the x naught approximately. Then the sequence becomes this one, that is yk equal to a into xk. Therefore, xk equal to maximum of x of k, that it will be converged to a dominant eigenvector v1 and the eigenvalue lambda 1 respectively. Therefore, limit xk k tends to infinity, that is equal to v1, at limit 6k k tends to infinity, that is equal to lambda 1. The rate of convergence of power method depends upon how the fast ratios go to 0, that is lambda. Therefore, the power method may converge slowly when the roots are very much closer and hence we would like to accelerate the convergence by some other techniques. Algorithm 1, the power method. To approximate the dominant eigenvalues and associate with an eigenvector of the n by n matrix A, and given that it is a non-zero vector x. Therefore, the input values are n, that is the dimension, and A the matrix, x the vector, and TOL tolerance. Then maximum number of iterations capital N. Output, we get the output step 1, that is step 2, then step 3, step 6 and 7, step 8 and 9, and 10, 11, 12. The output is maximum number of iteration exceeded. The procedure completely unsuccessfully, therefore stop. Next, second method, Wilkinson's method. Suppose that all the eigenvalues are real, but that the power method is converging slowly because there are two eigenvalues nearly equal in magnitudes. By the theory of eigenvalues, we know that n, a minus ql have same eigenvectors. If lambda is the eigenvalue of A, then lambda minus q is the eigenvalue of A minus qi. And the eigenvector in both cases being the same. Therefore, the optimal choices of q, if we wish to converge to lambda, is that the value which minimize. Using power method by a judicious choice of q, it may be possible to speed up the convergence markedly. The optimum value of q is lambda 2 plus lambda n, where lambda n is the smallest eigenvalue of A. Then, if we choose q equal to lambda n, there is also improved rate of convergence. We can have the maximum rate of convergence to lambda 1 minus q. Therefore, the choice of q depends on the eigenvalues lambda 1, lambda 2, etc. lambda n of the given matrix A. Third one, Aitken's method. Therefore, this process uses the form of mu minus mu the whole square, which is approximation to the greatest eigen value. Then mu1 and mu naught and mu are the eigenvalues in the first step, the second step, and the third step respectively, which are obtained from the power method. This is applicable to any linearly convergent sequence. The rate of convergence of this method, symmetric matrices. Then algorithm 3.